Okay. Welcome to 4C, even and odd symmetry. And we'll look at, determining whether a function is even or odd. In a nutshell, if f of x, if f of negative x equals f of x, or if f of x equals f of negative x, then the function is even. And if f of x does not equal f of negative x, then it's odd. Or it's the opposite of that, I'm pretty sure. So it's correct. Yeah, no, it's definitely that. Look at this. It has been said that all mathematics is the study of symmetry. Two simple types of symmetry often occur in functions. So of course, in functions of this course, that every function should be tested routinely for them. Cool. So even functions and lines of symmetry in the y-axis. A relation or a function is called even if its graph has a line symmetry in the y-axis, namely the y-axis is the line of symmetry. And this means that the graph is unchanged by reflection around the y-axis, as with the graph to the right. So if we reflected that graph here around the y-axis, we would get the same thing. Heck. All right. Goodness gracious. As explained in 4b, when we graph the function y equals f of x, when the graph of that function y equals f of x is reflected around the y-axis, then the new curve has the equation y equals f of negative x. But if y equals f of x and y equals negative x equal the same thing, then it would be even. So hence, for a function to be even, the graphs of y equals f of x and y equals f of negative x must coincide and literally be the same thing for all x in the domain. So that makes sense. Cool. And that's essentially the takeaway point from that. A relation or a function is called even if it has a y-axis as a line of symmetry, and namely, or algebraically, if f of x equals f of negative x, then they're the same thing. Odd functions, the opposite. An odd function, f of negative x will equal negative f of x. Then that's the odd function. So a relation or a function is called odd if its graph has a point of symmetry, in the origin. So this means that the graph is unchanged on a rotation of 180 degrees about the origin, or equivalently by successive reflections in all x-axis and y-axis. If you recall the class we did before the test, we looked at if we reflect about the x-axis and about the y-axis, that was the same as rotating the graph 180 degrees. And so, yeah, that's rotating 180 degrees. So if you have y equals f of x, and then if you reflected that around the x-axis, that would be y equals f of, on the y-axis, one of the axes, y equals f of negative x, and then if you reflected around the other axis, it would be negative y equals f of negative x. And so on and so forth. You get the end result there that f of negative x, if that is equal to negative f of x, then you have a odd function. The whole thing, which makes sense. Like, if we have y equals x squared, and we input, negative x into that, well, negative x squared is the same as x squared, as long as the substitution's in brackets, which it is. But if you had x cubed, you would get a result of, well, we'll just do it real quickly. So if f of negative x, if f of x equals x to the power of 3, then f of negative x would equal negative x to the power of 3, which clearly equals negative x to the power of 3, which equals negative of f of x. Does that make sense? A little bit. Josh is a bit right now. So I'm not saying that these are the same thing, like the result will be the same. Essentially what's happened is I've cubed negative 1, the negative 1 being cubed now, so the cube is applying to it, but the result of the negative 1 cubed is negative 1. So that comes out. And then now the only thing still waiting to be cubed is the x. And then if I look at compare this and this, then clearly the only difference between that and that is that there's a negative outside of the function. So it's the same as negative of f of x. Right. Odd functions and point symmetry in the origin. This is just the notes basically stating, wait, is it? Yeah, stating what we've just said. Josh, question? What was your statement? I disagree. I don't think it's objectively good or bad. It's just, it is. Yeah. Okay. Just for the record, Josh is stating his opinion is always right. Let's enjoy the contradiction of that. Yeah. Well, actually, that could be a true statement. You could say, I think you're wrong, and that may be the case, but that doesn't make your thought correct. It's just that you stating that you think that someone's wrong could be the actual case. Okay, enough of that. So testing functions algebraically for evenness and oddness. This is fortunately not super complex. Oh, look, some other people have joined us. That's great. Grace is not there. Claudia has joined us. Ben is there. William is there. Mason is there. Mike's there. Nick's there. And Mr. Thompson is there. Mr. Thompson? He teaches years 7 and 8. He can hear you. He's just having a look. Doesn't matter.
So would this be even, odd, neither?
Probably. Captain Obvious, thank you. We'll just go through. Yeah, no, that's good. Okay, so we're going to test each of these. So test each function for evenness or oddness. So part A, we've got f of x clearly equals x to the 4 minus 3. Now, if I want to say f of negative x, well, let's test that. That would equal negative x to the 4 minus 3, and that's clearly, now if I apply that fourth root, so I'm going to break it down very simply now. This is the same as saying negative 1 times x to the power of 4 minus 3, right? Which is the same as saying negative 1 to the power of 4 times x to the power of 4 minus 3, yeah? And that's clearly equal to 1 x to the power of 4 minus 3, which is clearly equal to x to the 4 minus 3. Is that okay? Okay. This is the same as this. Therefore, f of negative x equals f of x implies f of x is even. I'm not going to go into this much detail for all the other ones. It's a bit trivial, but that's the whole thing there. Part B. Oh, well, that's it. It's even or it's odd. That one's even. So part B, x to the 3. Okay, well, if f of x equals x to the power of 3, then f of negative x, as I demonstrated before, equals negative x to the power of 3. And that, if negative 1 has a cube, is negative 1 cubed, is still negative 1. So that's the same as saying negative of x to the power of 3. So clearly f of x is not equal to f of negative x. But what can I say about it? Let me just move this for a second. So, because remember, it's not a matter of proving neither. I can say, well, this is equal to negative of f of x. So that's actually a bad thing to state there. I'd say, therefore, f of x is odd. Now, I think the last one we're going to get to is going to be a case of it's not going to be either of those things. So the result will neither be f of x nor negative f of x, and then it would be neither even nor odd, which essentially means not a reflection about the y-axis, nor is it a complete rotation of 180 degrees of itself. Yeah. Okay. So let's do part C there. Again, if someone has a question, you just got to speak up. But if you're fine, then that's all good. Okay. Grace has joined. Welcome, Grace. You can press spacebar to talk briefly, or you can unmute yourself. Okay, f of, let's move this up. Wait, is Mr. Thompson still there? Where? I think he left. Okay, so f of x equals x squared minus 2x. Then f of negative x would equal negative x squared minus 2 of negative x. Well, that's clearly going to be x squared, but this is going to be plus 2x. It's a different thing, yeah. It's not, unfortunately, that is not equal to f of x or negative f of x. Because negative f of x would have been negative x squared plus 2x. But our x squared is positive, therefore neither even nor odd.
I was right.
Well done, Michael.
Thank
Good
you.
work. No, it was good work. Did they ask us? Oh, they asked us to sketch it. Yay, let's sketch it. Let's not. We can copy them in. Well, if you want to sketch it, then you've got to. Firstly, let's factorize. Let's factorize this x to the 4 minus 3. What's that going to look like? Well, that's going to be x squared minus the square root of 3 squared. Difference of 2 squares. Great. So that's going to be x squared minus root 3, x squared plus root 3. And that we can't do anything about, but this one we can. That's going to be, I mean, it doesn't really matter. you know that, like, we can't do anything about that because that's not going to be a 0. This one here, I just need, what is it? Square root. Yeah, it's the cubed root. So clearly, I mean, that's going to simplify to be x minus the 4th root of 3. Why wouldn't I 4th root it? I have to square root. Okay, so if I want to, sure. So this is the same as saying x squared minus square root of 3, square root of the square root of 3 squared, right? The square root of a square root is a 4th root. Yeah. Good question, that's okay. So it's that, and then x plus the 4th root of 3, and then x squared plus root 3. Great. So clearly then from these two things, I can say x is equal to the 4th root of 3 and the negative 4th root of 3. Okay. So those are my two roots, and you'd end up with a function, something like that, obviously a bit flatter at the bottom. Not really like that either, but anyway, negative 3, and then we've got the 4th root of 3, the negative 4th root of 3, and nothing else up there, I guess. That's just 3 points there. B and C, you guys can do it. Have fun. And enjoy. Yes, it is. 4th root of 3 is the number. Yeah, it is. 4th root of 3. It's 1.316. It's just it's not a rational number, you're right, but it is a real number. Yeah. Yep. Yeah, the only things that aren't real are the results from that. Like, there's no, that's irrational. I mean, that's not irrational. Sorry, that's not real. It would be I. It would be the 4th root of 3i. It would be. So that's it, we're done. I'm going to stop recording on that, but the class